What if the key to exploring distant galaxies lies not in centuries-long voyages, but in bending the very fabric of space and time? Faster-than-light travel has captivated scientists and dreamers alike, offering a tantalizing glimpse into a future where the stars are within our reach. For decades, it seemed like the stuff of science fiction, but groundbreaking theories are now reshaping our understanding of what might be possible. From the mind-bending possibilities of wormholes to the revolutionary concept of warp drives, these ideas are no longer confined to the pages of novels or the frames of movies. They're being explored by some of the brightest minds in physics, challenging everything we thought we knew about the universe. In this video, we'll uncover 30 astonishing theories that could transform interstellar travel from a distant dream into a tangible reality. Get ready to dive into the extraordinary, where the boundaries of science and imagination blur, and the cosmos becomes a playground of infinite possibilities. The speed of light, nearly 300,000 kilometers every second, isn't just a number. It's a fundamental boundary woven into the fabric of the universe itself. But why does this cosmic speed limit matter so much? To answer that, we need to look back to Albert Einstein's theory of relativity, which reshaped our understanding of space, time, and motion. According to Einstein, as an object approaches the speed of light, its mass increases exponentially, requiring infinite energy to go any faster. This isn't just a theoretical quirk, it's a hard stop, a barrier that seems to say, this far and no further. Now imagine the implications for space travel. Even at the speed of light, reaching the nearest star system, Alpha Centauri, would take over 4 years. And that's just our cosmic backyard. To cross the vast expanse of the Milky Way, which spans over 100,000 light-years, would take longer than human civilization has existed. The sheer scale of these distances makes traditional space travel, even with advanced propulsion, seem almost futile, but here's where things get fascinating. While the speed of light barrier might feel like a cosmic roadblock, it's also a challenge that has sparked some of the most creative and daring ideas in science. What if there's a way to bypass this limit entirely? Or what if, instead of moving through space, we could manipulate space itself? These questions aren't just idle speculation. They're the driving force behind some of the most astonishing theories we'll explore next. Understanding this barrier isn't just about accepting limits, it's about finding ways to transcend them. What if the vast distances between stars weren't an obstacle at all, but instead just a fold in the cosmic fabric waiting to be bridged? Enter wormholes, those mysterious cosmic shortcuts that have long captured the imagination of scientists and storytellers alike. Known formally as Einstein-Rosen bridges, these theoretical tunnels through space-time could revolutionize the way we think about interstellar travel. Picture this space-time as a piece of paper. If you fold that paper and poke a hole through it, you've created a shortcut between two distant points. That's the basic idea behind a wormhole, a tunnel that connects two far-flung regions of the universe, allowing for travel that bypasses the vast emptiness in between. But how would this work in practice? The concept hinges on the idea that space-time isn't just a static backdrop. It's a dynamic, flexible fabric that can be bent, stretched, or even punctured. If a stable wormhole could be created, it might allow spacecraft to traverse enormous distances in the blink of an eye, at least from the perspective of those on board. This wouldn't involve breaking the speed of light. Instead, it would sidestep the need for traditional travel altogether. Of course, the devil is in the details. Creating and maintaining a wormhole is no small feat. One of the biggest challenges lies in stabilizing these cosmic tunnels. Wormholes, as predicted by general relativity, are incredibly unstable. They tend to collapse almost instantly unless held open by something extraordinary, like exotic matter. This theoretical substance possesses negative energy density, allowing it to counteract the natural tendency of the wormhole to pinch shut. The problem: exotic matter has never been observed in nature, and its existence remains purely speculative. Even if we could find or create exotic matter, there's another hurdle to consider: the sheer scale of energy required. Some calculations suggest that stabilizing a wormhole might demand amounts of energy comparable to that of an entire star. And let's not forget the potential dangers. What happens if something goes wrong mid-transit? Could a wormhole collapse while a ship is passing through, or would it lead to unpredictable destinations? These are questions that scientists are still grappling with. Despite the challenges, the allure of wormholes as a gateway to the stars remains irresistible. Could they one day become the interstellar highways of humanity, allowing us to explore distant galaxies without the constraints of time or distance? The answer lies somewhere between the realms of possibility and imagination, waiting for future breakthroughs to bring this cosmic dream closer to reality. What if the secret to faster-than-light travel isn't about moving through space, but reshaping it entirely? This is the core idea behind the Alcubierre Warp Drive, a concept that sounds like pure science fiction but is grounded in real physics. Proposed in 1994 by physicist Miguel Alcubierre, this revolutionary idea offers a way to bypass the speed of light barrier, not by breaking the laws of physics, but by bending the very fabric of space-time itself. Here's how it works. Imagine space as a flat sheet. Instead of trying to move across the sheet, the Alcubierre drive would compress the sheet in front of the spacecraft and stretch it out behind. The ship itself would sit inside a warp bubble, a region of flat space-time, effectively surfing on a wave of distorted space. From the perspective of those inside the bubble, the ship isn't moving at all, space is moving around it. This clever loophole means the spacecraft could, in theory, reach distant stars faster than light without ever accelerating to such speeds. But what makes this possible? The key lies in something called negative energy, a peculiar form of energy that, unlike anything we're familiar with, exerts a repulsive force rather than an attractive one. Negative energy would be needed to create and sustain the warp bubble, bending space in the required way. Think of it like a cosmic treadmill. The space in front of the ship is pulled closer, while the space behind is pushed away, propelling the ship forward. The challenges, however, are immense. First, negative energy remains purely theoretical. While certain quantum effects, like the Casimir Effect, hint at its existence, we've yet to find a way to generate it in meaningful quantities. Second, the energy requirements are staggering. Early estimates suggested that creating a warp bubble might require the equivalent of the mass energy of an entire planet, or even a star. Though more recent calculations have reduced this figure, it's still far beyond our current capabilities. And then there's the question of stability. How do we ensure the warp bubble doesn't collapse mid-journey? What happens to the space-time around the bubble as it moves? These are just a few of the unresolved issues that make the Alcubierre drive a tantalizing yet distant possibility. Despite these hurdles, the Alcubierre Warp Drive represents a bold and imaginative approach to interstellar travel. It challenges us to think beyond traditional propulsion methods and consider the universe not as a fixed stage, but as a dynamic, malleable landscape. Could this be humanity's ticket to the stars? While the answer remains uncertain, the journey of exploration, both scientific and philosophical, is undeniably thrilling. What if the universe already has particles that break the cosmic speed limit, particles that don't just flirt with the speed of light but soar far beyond it? Enter tachyons, the hypothetical faster-than-light particles that have fascinated physicists for decades. Unlike everything else we know, tachyons are theorized to exist only at speeds greater than light, flipping our understanding of motion and energy on its head. These particles aren't just a curiosity, they could hold the key to unlocking entirely new ways of thinking about space, time, and communication across the cosmos. So, what makes tachyons so unique? According to the theory, these particles would have some bizarre properties. For starters, as they accelerate, their energy decreases, a complete reversal of how ordinary matter behaves. And here's where it gets even stranger. Tachyons would be impossible to slow down to the speed of light. If they existed, they'd always be faster, as if the speed of light were a floor instead of a ceiling. This peculiar behavior has led some to speculate that tachyons might not interact with normal matter in the ways we're used to, making them incredibly difficult to detect if they exist at all. But why are scientists so intrigued by the idea of tachyons? One possibility is their potential for faster-than-light communication. Imagine sending a message across the galaxy instantaneously, bypassing the frustrating delays imposed by the speed of light. Tachyons, if they could be harnessed, might offer a way to break this barrier, enabling real-time communication between distant star systems. This isn't just about convenience, it could fundamentally change how we explore and connect with the universe. Of course, the big question remains, do tachyons actually exist? Despite decades of searching, there's been no experimental evidence to confirm their presence. Some theories suggest that tachyons might be inherently undetectable, existing only as mathematical curiosities rather than physical entities. Others argue that their existence would disrupt the very foundations of physics, potentially leading to paradoxes like backward time travel or violations of causality. Yet, the tantalizing possibility of tachyons keeps researchers exploring. Could these elusive particles be hiding in the cosmic shadows, waiting for the right moment to reveal themselves? Or are they simply a fascinating quirk of theoretical physics, a reminder of how much we still have to learn about the universe? Whether real or imagined, tachyons challenge us to think beyond the limits of what we know, pushing the boundaries of science and imagination alike. As we ponder the mysteries of tachyons, one thing becomes clear: the universe is full of surprises, and sometimes the most extraordinary ideas begin as whispers in the dark. Could these hypothetical particles be the key to unlocking faster-than-light travel? Or are they just another piece of the cosmic puzzle, waiting for us to fit it into place? The journey to find out is as thrilling as the destination itself. What if the key to communicating across the vastness of space lies not in moving through it, but in a strange and spooky connection that defies our understanding of distance itself? This is the realm of quantum entanglement, a phenomenon so bizarre that even Albert Einstein famously called it spooky action at a distance. At its core, quantum entanglement occurs when two or more particles become linked in such a way that the state of one instantly influences the state of the other, no matter how far apart they are. This instantaneous connection seems to bypass the constraints of space and time, offering a tantalizing glimpse into a universe where information might travel faster than light. Let's break this down. Imagine two entangled particles, let's say electrons created together in a lab. If you measure the spin of one electron and find it spinning clockwise, the other electron, even if it's on the other side of the galaxy, will instantly spin counterclockwise. This connection happens faster than light could ever travel between them. It's as if the universe has a hidden phone line, allowing these particles to talk to each other without any delay. But here's the catch: while entanglement allows for instantaneous correlation between particles, it doesn't let us send information faster than light, at least not in the traditional sense. The reason lies in the randomness of quantum states. When you measure one particle, the outcome is unpredictable, meaning you can't control what message is being sent to the other particle. It's like having a pair of magic dice that always show opposite numbers, but you can't choose which numbers appear. Despite this limitation, scientists are exploring ways to harness entanglement for practical applications. One promising idea is quantum communication, where entangled particles could be used to create unbreakable encryption keys. This technology could revolutionize how we transmit sensitive information across vast distances, ensuring that messages remain secure even over interstellar scales. And then there's the bigger picture. What does quantum entanglement tell us about the nature of space and time? If particles can influence each other instantaneously, does that mean space is somehow interconnected in ways we don't yet understand? Could this phenomenon hint at a deeper layer of reality, where the boundaries between here and there, now and then, are more fluid than we ever imagined? While quantum entanglement may not directly solve the problem of faster-than-light travel, it opens up a world of possibilities for rethinking how we communicate and explore the cosmos. It challenges us to look beyond the familiar rules of physics and consider a universe where the impossible might just be waiting to be discovered. Could this mysterious quantum link be the first step toward a future where humanity reaches out to the stars in ways we can barely comprehend today? The answers may lie in the strange, spooky connections that bind the fabric of reality itself. What if the universe offered a way to not only travel faster than light, but also to bend time itself, allowing you to return home before you even left? This is the extraordinary idea behind Krasnikov tubes, a theoretical construct that could turn science fiction into reality. Proposed by physicist Sergei Krasnikov in the 1990s, these tubes are a type of space-time shortcut that could enable faster-than-light travel while also opening the door to time travel. But how does this work, and what does it mean for the future of interstellar exploration? Picture this. A spacecraft embarks on a journey to a distant star, creating a Krasnikov tube as it goes. This tube isn't a physical structure but a warped region of space-time, shaped like a tunnel that stretches from the starting point to the destination. Once the tube is established, the return trip becomes instantaneous, thanks to a phenomenon known as a closed time-like curve. In simpler terms, the spacecraft could return to its origin before it even began its journey, effectively allowing it to travel back in time. The implications of such a technology are as thrilling as they are mind-bending. Imagine being able to explore distant galaxies and return home in the same moment you left. Or consider the possibilities for communication. Messages sent through a Krasnikov tube could arrive before they were even sent, creating a feedback loop of information. But with these possibilities come profound challenges. Time travel, even in theory, raises questions about causality and paradoxes. What happens if you return to the past and alter events that shaped the future? Could you create a universe where you never left in the first place? One of the most famous thought experiments in this realm is the grandfather paradox, where a time traveler prevents their own existence by altering the past. Krasnikov tubes, while not explicitly creating such paradoxes, do exist in a gray area where the rules of cause and effect become blurred. Some physicists argue that the universe might have built-in mechanisms to prevent such paradoxes, while others suggest that alternate timelines or parallel universes could resolve these contradictions. But the challenges don't end with philosophy and paradoxes. Building a Krasnikov tube would require unimaginable amounts of energy and technology far beyond our current capabilities. The process would involve manipulating spacetime on a scale that's difficult to even conceptualize, let alone achieve. And even if we could create such a tube, there's no guarantee it would remain stable or safe for travel. Despite these hurdles, the concept of Krasnikov tubes pushes the boundaries of what we think is possible. It challenges us to rethink not only how we move through space, but also how we perceive time itself. Could these theoretical constructs one day become the highways of the cosmos, connecting distant stars and eras in ways we can scarcely imagine. As we explore these ideas, we're reminded that the universe is far stranger and more wondrous than we often assume. Krasnikov tubes may be a distant dream, but they inspire us to keep asking questions, pushing limits, and dreaming of a future where the stars, and perhaps even time itself, are within our grasp. What if the most dangerous objects in the universe could become humanity's greatest allies in the quest for interstellar travel? Black holes, often seen as cosmic monsters that devour everything in their path, might hold the key to unlocking unprecedented speeds for spacecraft. This daring concept, known as the black hole slingshot, turns the immense gravitational pull of these celestial giants into a potential tool for propulsion. By harnessing the raw power of gravity, we could accelerate ships to velocities approaching the speed of light, opening up the possibility of exploring the farthest reaches of our galaxy and beyond. The idea revolves around a technique called a gravity assist, something we already use on a smaller scale with planets. For example, spacecraft like Voyager 1 and 2 have used the gravity of Jupiter to gain speed, effectively borrowing energy from the planet's motion. But with black holes, the scale is on an entirely different level. Their gravitational fields are so intense that a spacecraft could theoretically slingshot around them, gaining a massive boost in velocity. Imagine a ship skimming just outside the event horizon, where gravity is at its strongest and being flung outward at a fraction of the speed of light. It's like using a cosmic catapult with the black hole as the ultimate launch pad. Of course, this isn't without its challenges and dangers. One of the biggest risks is tidal forces. Black holes exert such extreme gravitational gradients that the pull on one side of a spacecraft could be vastly stronger than on the other. This difference, known as spaghettification, could stretch and tear the ship apart if it gets too close. To avoid this, the slingshot maneuver would need to be executed with incredible precision, staying within a narrow zone where the gravitational forces are manageable but still powerful enough to provide a significant boost. Then there's the mind-bending effect of time dilation. As Einstein's theory of relativity predicts, time slows down near a black hole due to its intense gravity. For the crew on board, a close pass might feel like only a few minutes, while years or even decades could pass for observers back on Earth. This raises fascinating questions about the nature of time and the practicalities of interstellar travel. Would the crew return to a world that has moved on without them, or could this effect be harnessed to make long journeys seem shorter from the traveler's perspective? Despite these challenges, the black hole slingshot concept is more than just a wild idea. It's a testament to humanity's ingenuity and our ability to find opportunity even in the most extreme environments. Could black holes, once seen as insurmountable obstacles, become the stepping stones to the stars? While the technology and understanding needed to pull this off are still far beyond our reach, the very possibility pushes us to rethink what's achievable. After all, the universe is full of surprises, and sometimes the most daunting challenges hide the most extraordinary solutions. As we continue to explore the frontiers of physics and engineering, the black hole slingshot stands as a bold reminder that the cosmos is not just a place of limits, but also a realm of untapped potential. Who knows, one day these gravitational behemoths might not just be the keepers of cosmic mysteries, but the gateways to new worlds. What if the power to travel to the stars could come not from engines or fuel, but from beams of light? This is the revolutionary idea behind laser-powered light sails, a concept that could transform how we explore the cosmos. Unlike traditional rockets, which rely on chemical propulsion, light sails harness the gentle but relentless push of photons, the particles of light. By reflecting these photons off a vast, ultra-thin sail, a spacecraft could gradually build up incredible speeds, potentially reaching a significant fraction of the speed of light. One of the most exciting projects in this field is Breakthrough Starshot, a bold initiative aiming to send a fleet of tiny probes to Alpha Centauri, our nearest stellar neighbor. These probes, each no larger than a smartphone, would be equipped with light sails and propelled by an array of ground-based lasers. Once launched, the lasers would focus an intense beam of light onto the sails, accelerating the probes to speeds of up to 20% of the speed of light. At that pace, the journey to Alpha Centauri, a trip that would take thousands of years with current technology, could be completed in just over 20 years. But how does this technology work? The key lies in the interaction between light and the sail. When photons strike the reflective surface, they transfer a tiny amount of momentum to the sail, pushing it forward. Over time, this constant push can add up to tremendous speeds, especially when amplified by powerful lasers. The sails themselves are made of incredibly lightweight materials, often just a few atoms thick, to maximize their efficiency. It's a delicate balance. The sails must be strong enough to withstand the laser's intensity, yet light enough to be propelled by its force. Scaling this technology up for human travel, however, presents a host of challenges. For starters, the energy requirements are staggering. A manned mission would need sails the size of cities and lasers with power outputs far beyond anything we currently possess. Then there's the issue of deceleration. How do you slow down a spacecraft traveling at such incredible speeds? Current designs for light sails focus on one-way trips, making them ideal for probes but impractical for crewed missions. Despite these hurdles, the potential of laser-powered light sails is undeniable. They offer a way to explore distant stars without the need for massive fuel reserves or decades-long voyages. And while they may not break the speed of light, they bring us closer to the dream of interstellar travel than ever before. Could this be the first step toward a future where humanity reaches out to the stars, not with rockets but with beams of light? As we continue to refine this technology, we're reminded that sometimes the most groundbreaking ideas come from the simplest principles. Riding on beams of light, we might one day find ourselves exploring worlds that once seemed impossibly out of reach. The stars are calling, and with light sails, we might just have the answer. What if the ultimate source of energy for interstellar travel has been hiding in plain sight all along, not in distant stars or exotic materials, but in the very fabric of the universe itself? Enter antimatter, the mysterious counterpart to ordinary matter, and one of the most energy-dense substances known to science. When matter and antimatter meet, they annihilate each other in a burst of pure energy, a process so efficient that just 1 gram of antimatter could release the same amount of energy as 20 kilotons of TNT. This staggering potential makes antimatter propulsion one of the most tantalizing prospects for achieving near light-speed travel, bringing distant stars within reach of human exploration. So, how does antimatter propulsion work? At its core, it's about harnessing the immense energy released during annihilation. In a spacecraft equipped with an antimatter engine, tiny amounts of antimatter will be directed to collide with matter, creating a controlled explosion. The resulting energy could then be channeled into a propulsion system, accelerating the ship to incredible speeds. Unlike chemical rockets, which rely on inefficient combustion, antimatter propulsion offers a direct conversion of mass into energy, as described by Einstein's famous equation, E equals mc squared. This means far less fuel would be needed to achieve the same thrust, making it an ideal candidate for long-distance space travel. But before we get too excited, there's a catch, or rather, several. The first challenge is producing antimatter in meaningful quantities. Currently, antimatter is created in particle accelerators, but the process is incredibly energy-intensive and expensive. To give you an idea, producing just 1 gram of antimatter would require decades of operation from the world's most powerful accelerators, at a cost of trillions of dollars. Even then, storing antimatter is no simple task. because it annihilates upon contact with ordinary matter. It must be contained in ultra-high vacuum chambers and held in place by powerful magnetic fields, technologies that are still in their infancy. Then there's the issue of safety. Antimatter is as dangerous as it is powerful. A single mishap in containment could lead to a catastrophic release of energy, posing risks not just to the spacecraft but potentially to entire missions. And while the energy density of antimatter is extraordinary, the radiation produced during annihilation could also pose significant hazards to both equipment and crew. Despite these hurdles, the potential rewards are too great to ignore. Antimatter propulsion could reduce travel times to nearby star systems from millennia to mere decades, opening up the galaxy to human exploration in ways we can barely imagine. Imagine setting foot on a distant exoplanet, not as a distant dream, but as a tangible goal within our lifetimes. The journey to harness antimatter is as much about pushing the boundaries of science as it is about redefining what's possible. While the challenges are immense, they remind us that the greatest breakthroughs often come from tackling the toughest problems. Could antimatter be the fuel that propels humanity to the stars? The answer lies in the delicate balance between ambition and innovation, as we strive to unlock the secrets of the universe one particle at a time. What if the key to reaching distant stars wasn't just about speed, but about bending time itself? This is the mind-bending reality of time dilation, a phenomenon rooted in Einstein's theory of relativity. As an object accelerates closer to the speed of light, time for that object slows down relative to everything else. For astronauts aboard a spacecraft traveling at such incredible velocities, this means they could experience a journey of just a few years, while decades or even centuries pass by on Earth. It's like stepping into a cosmic time machine where the rules of aging and time itself are rewritten. Let's unpack this idea with an example. Imagine a spacecraft accelerating to 90% of the speed of light, heading for a star system 50 light-years away. From the perspective of someone on Earth, the journey would take just over 50 years, accounting for the distance and the time it takes light to travel. But for the astronauts on board, thanks to time dilation, the trip might feel like only 20 years. They'd arrive at their destination younger than their counterparts back home, having experienced time at a slower rate. This isn't just theoretical. Time dilation has been proven in real-world experiments. Atomic clocks on fast-moving jets or orbiting satellites, for instance, tick slightly slower than those on the ground. While the effect is minuscule at everyday speeds, it becomes dramatic as velocities approach the speed of light. For interstellar travel, this phenomenon could be a game-changer. Astronauts could potentially reach distant stars within their lifetimes, even if centuries have passed on Earth. But with this incredible possibility come profound questions. What would it mean for families and societies if space travelers returned to a world that had moved on without them? Could humanity adapt to the idea of explorers leaving one era and returning to another? These aren't just scientific challenges, they're deeply human ones, touching on the ethics of time and the bonds that connect us. And then there's the practical side. Could we harness time dilation to make faster-than-light travel a reality for those on board? While the travelers themselves might experience shorter journeys, the rest of the universe would still operate under the constraints of light speed. This means that from Earth's perspective, the trip would still take decades or more. Time dilation doesn't change the speed of light, it changes how time is experienced. Yet, the implications are staggering. For civilizations looking to explore the galaxy, time dilation could offer a way to bridge the vast distances between stars without waiting for generations. It's a reminder that the universe is far stranger and more flexible than we often assume. Could this phenomenon be the key to unlocking the stars for humanity? Or will the challenges of time and distance remain insurmountable? As we ponder these questions, one thing is clear. time dilation isn't just a quirk of physics, it's a window into the extraordinary possibilities of the cosmos. It challenges us to rethink not only how we travel, but how we understand the very fabric of time itself. And in that challenge lies the spark of discovery, pushing us ever closer to the stars. What if the universe itself holds a hidden energy source, one so vast and powerful that it could reshape the way we think about faster-than-light travel? Dark energy, the mysterious force driving the accelerating expansion of the cosmos, might just be the key to unlocking this extraordinary possibility. Unlike anything we've encountered before, dark energy makes up roughly 68% of the universe, yet it remains one of the greatest enigmas in modern science. Its presence is inferred from the way galaxies are being pushed apart at ever-increasing speeds, but what it is and how it works are questions that continue to baffle researchers. One of the most intriguing ideas surrounding dark energy is its potential to manipulate space-time itself. Imagine if we could tap into this cosmic force to create warp bubbles, regions of distorted space-time that allow spacecraft to travel faster than light without actually breaking the speed limit. This concept ties back to the Alcubierre Warp Drive, where space is compressed in front of a ship and expanded behind it. But instead of relying on hypothetical negative energy, could dark energy provide the necessary power to bend space-time in such a dramatic way? The challenges, however, are immense. For starters, dark energy is incredibly diffuse, spread thinly across the universe. Concentrating it enough to create a warp bubble would require technology far beyond our current capabilities. And then there's the issue of control. Dark energy's effects are subtle on a local scale, but they dominate the universe on cosmic scales. Harnessing it would mean understanding and manipulating a force that, at present, we can barely detect. Some theories suggest that dark energy might be connected to the vacuum of space itself, a property inherent to the fabric of the universe. If that's the case, then controlling it could involve manipulating the very structure of space-time. This raises fascinating questions about the nature of reality and how far we can push the boundaries of science. Could dark energy be the ultimate power source, not just for interstellar travel, but for reshaping the cosmos itself? Despite the uncertainties, the potential is too compelling to ignore. If we could harness dark energy, it might offer a way to bypass the limitations of conventional propulsion, opening up the galaxy to exploration on an unprecedented scale. The journey to understand this mysterious force is as much about unraveling the secrets of the universe as it is about redefining what's possible for humanity. As we peer into the vast expanse of the cosmos, dark energy stands as a reminder that the universe is full of surprises. It challenges us to think beyond the limits of our current knowledge and imagine a future where the stars are no longer out of reach. Could this enigmatic force be the key to unlocking faster-than-light travel? The answer lies in the mysteries waiting to be uncovered, and the journey to find them is as thrilling as the destination itself. What if the key to faster-than-light travel lies not in brute force, but in the strange, almost magical behavior of particles at the quantum level? This is where quantum tunneling comes into play, a phenomenon so counterintuitive that it seems to defy the very laws of classical physics. In the quantum world, particles don't always follow the rules we're used to. Instead of being stopped by barriers, they can sometimes pass right through them, as if the obstacle simply didn't exist. This bizarre behavior, known as quantum tunneling, could hold the key to unlocking entirely new ways of moving through space and time. To understand how this works, let's break it down. Imagine you're standing at the base of a mountain and you need to get to the other side. In the classical world, you'd have to climb over it, a task that requires energy and effort. But in the quantum world, there's a chance you could simply pass through the mountain, emerging on the other side without ever scaling its peak. This isn't science fiction. It's a well-documented phenomenon observed in everything from electrons to atoms. Now apply this idea to space travel. What if a spacecraft could use quantum tunneling to jump through space-time barriers, bypassing the vast distances between stars? Instead of traveling through the emptiness of space, the ship could tunnel through a kind of cosmic shortcut, reaching its destination in a fraction of the time. This concept, while still theoretical, could revolutionize propulsion systems, offering a way to reduce travel times without the need for massive amounts of energy. But how could this be achieved? One possibility lies in manipulating the fabric of space-time itself. If we could create conditions where quantum tunneling becomes possible on a macroscopic scale, something far beyond our current capabilities, we might enable spacecraft to pass through barriers that would otherwise be insurmountable. Think of it as creating a temporary hole in space-time, allowing the ship to slip through to its destination. Of course, the challenges are immense. Quantum tunneling typically occurs at the subatomic level, and scaling it up to the size of a spacecraft would require breakthroughs in both physics and engineering. There's also the question of stability and control. How do we ensure that the tunneling process is precise and safe for the crew and equipment on board? Despite these hurdles, the potential is too exciting to ignore. Quantum tunneling offers a glimpse into a universe where the impossible becomes possible, where barriers are no longer obstacles but gateways to new frontiers. It challenges us to rethink how we approach space travel, moving beyond traditional propulsion methods and embracing the strange, beautiful world of quantum physics. Could this phenomenon be the secret to unlocking faster-than-light travel? While the answer remains uncertain, the journey to explore its possibilities is a testament to humanity's relentless curiosity and ingenuity. As we delve deeper into the mysteries of the quantum realm, we're reminded that the universe is far stranger and more full of potential than we ever imagined. What if the universe we see is just a fraction of the whole story, a mere slice of a much larger, multidimensional reality? This is the mind-expanding idea behind hyperspace, a theoretical realm that exists beyond the three dimensions of length, width, and height that we're familiar with. By venturing into these higher dimensions, some scientists believe we could unlock a shortcut through the cosmos, bypassing the vast distances of our universe and making faster-than-light travel not just possible but practical. To understand hyperspace, let's start with a simple analogy. Imagine a flat, two-dimensional world like a piece of paper. For creatures living on that paper, moving from one point to another would mean traveling along the surface, following every curve and bend. But for us, living in three dimensions, it's easy to see a shortcut. Simply lift the paper and fold it, bringing the 2 points together. Hyperspace works on a similar principle, suggesting that if we could access higher dimensions, we might be able to fold our three-dimensional space, creating shortcuts that bypass the vast emptiness between stars. Mathematically, this idea is rooted in theories like string theory and M-theory, which propose that our universe might have as many as 10 or 11 dimensions. These extra dimensions are thought to be compacted or hidden, curled up so tightly that we can't perceive them in our everyday lives. But if we could somehow access them, they might offer a pathway through which we could travel vast distances in an instant. Think of it like a cosmic subway system where higher dimensions act as tunnels connecting distant points in our universe. The challenge, of course, lies in accessing these higher dimensions. For now, they remain purely theoretical, existing only in the equations of physicists and the imaginations of science fiction writers. One of the biggest hurdles is understanding how to uncurl these dimensions, making them large enough and stable enough for travel. Some theories suggest that immense amounts of energy, perhaps even the energy of an entire star, might be required to create a stable pathway through hyperspace. Others propose that exotic forms of matter or advanced technologies could be the key to unlocking these hidden dimensions. Then there's the question of navigation. If hyperspace exists, how would we map it? How would we ensure that a spacecraft traveling through higher dimensions arrives at the intended destination and not some random point in the universe? These are questions that push the boundaries of both physics and engineering, requiring breakthroughs that are still far beyond our reach. Despite these challenges, the concept of hyperspace is a tantalizing one. It challenges us to think beyond the limits of our three-dimensional world and imagine a universe that's far more complex and interconnected than we ever realized. Could hyperspace be the ultimate shortcut, the gateway to the stars that humanity has been dreaming of for centuries? As we explore these ideas, we're reminded that the universe is full of mysteries waiting to be uncovered. Hyperspace may be a distant dream, but it's a reminder that the cosmos is far stranger and more wondrous than we often assume. And in that strangeness lies the potential for discovery, pushing us to keep asking questions, keep exploring, and keep reaching for the stars. What if the energy to power faster than light travel was hiding in the empty void of space itself? This is the intriguing possibility offered by the Casimir Effect, a quantum phenomenon that reveals the hidden energy lurking in what we think of as nothingness. At its core, the Casimir Effect occurs when two uncharged, perfectly smooth plates are placed extremely close together in a vacuum. Under these conditions, an unexpected force arises between the plates, a force not caused by gravity, magnetism, or any traditional interaction, but by the quantum fluctuations of empty space. To understand how this works, let's dive into the strange world of quantum physics. Even in a vacuum, space is not truly empty. Instead, it's teeming with fleeting particles and antiparticles that pop in and out of existence, a phenomenon known as quantum fluctuations. These fluctuations create a kind of background energy, often referred to as vacuum energy. When two plates are brought close together, they limit the types of fluctuations that can occur between them, creating an imbalance. The result, the plates are pushed together by an invisible force, the Casimir Effect. Now, imagine harnessing this force for propulsion. If we could control and amplify the Casimir Effect, it might provide a way to manipulate space-time itself, creating a source of energy for faster-than-light travel. One idea is to use the effect to generate thrust without the need for traditional fuel. By creating arrays of microscopic plates and exploiting the forces between them, a spacecraft could potentially ride on the energy of the vacuum, achieving incredible speeds without the limitations of conventional propulsion systems. But the potential goes even further. Some researchers speculate that the Casimir Effect could be used to stabilize wormholes or even create warp bubbles, bending space-time in ways that make faster-than-light travel possible. The key lies in the ability to manipulate vacuum energy on a large scale, turning a quantum curiosity into a practical tool for interstellar exploration. Of course, the challenges are significant. For one, the Casimir Effect is incredibly weak at macroscopic scales, requiring precise engineering to generate meaningful amounts of force. Scaling it up to power a spacecraft would demand breakthroughs in materials science, nanotechnology, and energy conversion. Additionally, the effect is highly sensitive to the environment, meaning even the slightest imperfections or external interference could disrupt its application. Then there's the question of control. How do we direct the energy generated by the Casimir Effect in a way that's useful for propulsion? Current research is still in its early stages, and while the theoretical potential is immense, the practical hurdles are equally daunting. Despite these challenges, the Casimir Effect represents a fascinating frontier in the quest for faster-than-light travel. It reminds us that even the emptiest corners of the universe hold untapped potential, waiting for the right combination of curiosity and ingenuity to unlock their secrets. Could vacuum energy be the key to powering the starships of the future? While the answer remains uncertain, the journey to find out is a testament to humanity's relentless drive to explore the unknown. As we continue to probe the mysteries of quantum physics, the Casimir Effect stands as a reminder that the universe is full of surprises, and sometimes the most extraordinary solutions are hidden in the spaces we least expect. What if the universe has secret exits scattered across the cosmos, places where matter and energy don't disappear but burst back into existence? These are the enigmatic white holes, the cosmic counterparts to black holes. While black holes are known for their insatiable gravitational pull, swallowing everything that crosses their event horizon, white holes are theorized to do the exact opposite. They expel matter and energy, creating a cosmic fountain of sorts. Think of them as the universe's way of balancing the scales, offering an exit where black holes provide an entrance. The concept of white holes emerges from the same equations of general relativity that predict black holes. In theory, they're the other side of the equation, a region of space-time where nothing can enter, but everything is pushed outward. If a black hole is a one-way street into oblivion, a white hole is a one-way street out, spewing light, energy, and possibly even entire galaxies. It's an idea that feels almost poetic, as if the universe itself is built on a system of cosmic recycling. But how could white holes help us with faster-than-light travel? One intriguing possibility is that they could act as gateways, connecting distant parts of the universe through a kind of cosmic shortcut. Imagine a spacecraft entering a black hole, traveling through a hypothetical tunnel known as a wormhole, and emerging from a white hole in a completely different region of space. This would allow for instantaneous travel across vast distances, bypassing the constraints of light speed entirely. It's a concept that sounds like science fiction, but it's rooted in the same physics that describe black holes and wormholes. The challenge, of course, is that white holes remain purely theoretical. Unlike black holes, which we've observed indirectly through their gravitational effects and more directly with groundbreaking images like the one captured by the Event Horizon Telescope, white holes have never been detected. Some scientists argue that they may not even exist in our universe, or if they do, they might be incredibly rare or short-lived. Then there's the question of how we could harness them for travel. Even if white holes exist, their violent nature, spewing out energy and matter at incredible speeds, might make them too dangerous to approach. Could a spacecraft survive the torrent of radiation and particles being ejected from a white hole? And how would we navigate such a chaotic environment? These are just a few of the many hurdles that make white holes a tantalizing yet distant possibility. Despite these challenges, the idea of white holes continues to captivate scientists and dreamers alike. They challenge us to rethink the nature of space-time, pushing the boundaries of what we think is possible. Could these cosmic fountains one day become the gateways to interstellar exploration, allowing us to traverse the galaxy in the blink of an eye? Or are they simply a fascinating quirk of theoretical physics, a reminder of how much we still have to learn about the universe? As we ponder these questions, we're reminded that the cosmos is full of mysteries waiting to be unraveled. White holes may be elusive, but they inspire us to keep exploring, to keep questioning, and to keep dreaming of a future where the stars are no longer out of reach. What if the universe itself could provide a way to surf across the stars, not by pushing through space, but by riding the ripples of space-time itself? Gravitational waves, those faint, undulating ripples caused by the most violent events in the cosmos, like colliding black holes or neutron stars, might hold the key to a revolutionary form of interstellar travel. Detected for the first time in 2015 by the Laser Interferometer Gravitational Wave Observatory, or LIGO, these waves have opened up a new window into the universe. But beyond their role in observing cosmic collisions, could they also offer a way to propel spacecraft to incredible speeds, turning the fabric of space-time into a cosmic highway? To understand how this might work, let's start with what gravitational waves actually are. Imagine dropping a pebble into a still pond. The ripples that spread out are like gravitational waves, but instead of water, they're ripples in the very fabric of space-time. These waves carry energy across the universe, stretching and compressing space as they pass. Now, picture a spacecraft equipped with a kind of gravitational sail, designed to catch these ripples and ride them like a surfer on a wave. By harnessing the energy of gravitational waves, such a ship could potentially accelerate to astonishing velocities without the need for traditional propulsion systems. The idea isn't as far-fetched as it might sound. Gravitational waves are incredibly powerful at their source, capable of moving entire planets by tiny fractions of an inch as they pass through. The challenge lies in detecting and harnessing these waves, which are incredibly faint by the time they reach us. Current technology, like LIGO, can detect them, but it's not yet equipped to interact with them in a way that could propel a spacecraft. To make this a reality, we'd need advanced materials and engineering capable of capturing and converting these ripples into usable thrust. One of the biggest hurdles is the sheer scale of the waves. Gravitational waves are vast, often spanning light years, making it difficult to design a sail or device that could effectively catch them. Additionally, the waves are incredibly sparse, meaning a spacecraft might have to wait a long time between opportunities to ride them. This raises questions about how practical such a method would be for long-distance travel, especially when compared to other theoretical propulsion systems. But the potential is undeniable. If we could develop the technology to surf gravitational waves, it would open up a new era of space exploration. Ships could traverse the galaxy not by brute force, but by harmonizing with the natural rhythms of the universe itself. It's a concept that blends the elegance of physics with the audacity of human ingenuity, offering a glimpse of a future where the cosmos becomes not just a place to visit, but a partner in our journey. As we continue to study gravitational waves, we're reminded of how much we still have to learn about the universe. These ripples in space-time are more than just cosmic phenomena. They're a testament to the interconnectedness of all things, a reminder that even the most distant events can have a profound impact on our world. Could gravitational waves one day become the highways of the future, carrying humanity to the stars on waves of space-time itself? The answer lies in the mysteries waiting to be uncovered, and the journey to find them is as thrilling as the destination. What if the key to bending space-time and unlocking faster-than-light travel lies in a substance that defies everything we know about the physical world? Enter exotic matter, a theoretical material with properties so strange they seem to belong in the realm of science fiction. Unlike ordinary matter, which we interact with every day, exotic matter possesses something called negative energy density. This means it doesn't just resist gravity, it actively repels it, creating a kind of anti-gravity effect. It's this bizarre property that makes exotic matter essential for two of the most exciting concepts in faster-than-light travel: wormholes and warp drives. To understand why exotic matter is so crucial, let's revisit the idea of wormholes. These cosmic shortcuts, as we've discussed, are incredibly unstable. Without something to hold them open, they collapse almost instantly. That's where exotic matter comes in. Its negative energy density could counteract the natural tendency of a wormhole to pinch shut, effectively acting as a cosmic scaffolding to keep the tunnel stable. Similarly, in the case of warp drives, exotic matter would be needed to create and sustain the warp bubble, a region of distorted space-time that allows a spacecraft to travel faster than light without breaking the cosmic speed limit. But what exactly is exotic matter, and could we ever produce it? The concept stems from quantum physics, where particles can briefly exhibit strange behaviors like negative energy states. One example is the Casimir Effect, where two uncharged plates placed extremely close together in a vacuum experience an attractive force due to quantum fluctuations. This effect hints at the existence of negative energy, but harnessing it on a scale large enough to stabilize a wormhole or power a warp drive is a monumental challenge. The production of exotic matter would require technology far beyond our current capabilities. For one, we'd need to find a way to generate and sustain negative energy in significant quantities. Even then, the energy requirements would be staggering. Some estimates suggest that stabilizing a wormhole might demand energy equivalent to the mass of a star. And let's not forget the practical challenges of containing and controlling such a substance without it annihilating itself or wreaking havoc on the surrounding environment. Despite these hurdles, the potential applications of exotic matter are too compelling to ignore. If we could master its production and manipulation, it could revolutionize not just space travel but our understanding of the universe itself. Imagine being able to create stable wormholes connecting distant parts of the galaxy in an instant, or envision warp drives that allow us to explore the stars without the constraints of time or distance. These possibilities are no longer confined to the pages of sci-fi novels. They're the focus of serious scientific inquiry, but the implications go even deeper. Exotic matter challenges us to rethink the very nature of reality. What does it mean for a substance to have negative energy? Could this strange material hold clues to the fundamental forces that govern the cosmos? As we explore these questions, we're reminded that the universe is far stranger and more full of potential than we often assume. Could exotic matter be the key to unlocking the secrets of faster-than-light travel? The answer lies somewhere between the frontiers of science and the limits of our imagination. While the challenges are immense, the journey to understand and harness this mysterious substance is a testament to humanity's relentless curiosity and ingenuity. And in that journey, we may just find the tools to reach the stars and perhaps even rewrite the rules of the universe itself. What if the future of space travel didn't rely on massive fuel tanks or explosive propulsion systems, but instead on a technology so subtle it harnesses the very fabric of the universe? This is the promise of quantum vacuum thrusters, a concept that has sparked both excitement and skepticism in the scientific community. Known by its more popular name, the M-Drive, this technology claims to generate thrust without expelling any propellant, a feat that seemingly defies the laws of physics as we know them. But how does it work, and could it really pave the way for faster-than-light travel? At the heart of the M-Drive is an idea that sounds almost magical. It creates thrust by bouncing microwaves around inside a closed, cone-shaped cavity. According to the theory, the shape of the cavity causes the microwaves to exert more force on one end than the other, creating a net thrust. Unlike traditional rockets, which rely on Newton's third law, every action has an equal and opposite reaction. The M-Drive appears to generate movement without pushing anything out the back. It's as if you could move a boat by blowing air inside it, rather than using oars or a sail. The implications of such a technology are staggering. Without the need for propellant, spacecraft could become lighter, faster, and more efficient, capable of traveling vast distances without the logistical nightmare of carrying fuel. Missions to distant star systems, once deemed impossible due to the limitations of chemical propulsion, could suddenly become feasible. The M-Drive could even offer a way to maintain thrust over long periods, allowing for continuous acceleration and potentially reaching speeds that bring us closer to the dream of faster-than-light travel. But before we get too carried away, it's important to address the elephant in the room, the controversy surrounding the M-Drive. While some experiments have reported small but measurable thrust, others have failed to replicate the results. Critics argue that the observed thrust could be the result of experimental errors or external factors, such as thermal effects or electromagnetic interference. The scientific community remains divided, with some calling for rigorous, large-scale testing to confirm whether the M drive truly works or if it's a case of wishful thinking. Even if the M drive does produce thrust as claimed, scaling it up for practical use presents significant challenges. The thrust generated in experiments so far has been minuscule, barely enough to move a feather, and scaling it to propel a spacecraft would require breakthroughs in both energy efficiency and engineering. Additionally, the technology would need to operate reliably over long durations in the harsh environment of space, where even the smallest malfunction could jeopardize a mission. Despite these hurdles, the potential rewards are too tantalizing to ignore. If quantum vacuum thrusters could be perfected, they might revolutionize not just space travel, but our entire approach to exploring the cosmos. Imagine spacecraft that don't need to carry fuel, allowing them to travel farther and faster than ever before. Or consider the possibility of continuous thrust, enabling missions to distant stars that were once thought to be centuries away. The journey to validate and refine the M drive is a reminder of how science often operates at the edge of the possible. It challenges us to question our assumptions, push the boundaries of what we think is achievable, and remain open to ideas that seem to defy conventional wisdom. Whether quantum vacuum thrusters will one day propel humanity to the stars remains to be seen, but the pursuit of this technology is a testament to our unyielding curiosity and determination to explore the unknown. As we continue to probe the mysteries of the universe, the M drive stands as a symbol of the audacity of human ingenuity. It's a reminder that sometimes the most groundbreaking discoveries begin as whispers in the dark, waiting for the right combination of curiosity and courage to bring them into the light. Could this controversial technology be the key to unlocking the stars? The answer lies in the experiments yet to come and the questions we dare to ask along the way. What if the universe itself is woven with invisible threads, stretching across the cosmos like a vast network of superhighways? These are cosmic strings, hypothetical one-dimensional defects in the fabric of space-time that could revolutionize how we think about interstellar travel. Unlike wormholes or warp drives, cosmic strings don't require bending or folding space-time. Instead, they act as natural pathways, offering a direct route to distant corners of the universe. Imagine a ship traveling along one of these strings, bypassing the vast emptiness of space and arriving at its destination in what feels like an instant. To understand cosmic strings, let's start with their origins. These structures are thought to have formed in the early universe, moments after the Big Bang, as space-time cooled and underwent phase transitions. Picture it like water freezing into ice. As it solidifies, cracks and imperfections can form. In the same way, cosmic strings are like cracks in the fabric of the universe, remnants of a time when the cosmos was still taking shape. What makes cosmic strings so intriguing is their potential for faster-than-light travel. Because they are incredibly dense and under immense tension, they warp the space around them, creating regions where the rules of physics behave differently. A spacecraft traveling along a cosmic string could, in theory, move faster than light without actually violating Einstein's laws. It's not that the ship is accelerating to such speeds, it's that the space-time around the string is distorted, allowing for a kind of cosmic shortcut. But how would this work in practice? Navigating a cosmic string would require precise control and advanced technology. The string's immense gravitational field would need to be harnessed without tearing the ship apart, and the path along the string would have to be carefully calculated to avoid any unexpected detours. Think of it like riding a high-speed train through a mountain tunnel. The journey is fast and efficient, but only if the tracks are perfectly aligned and the train is built to handle the speed. One of the biggest challenges, however, is detecting cosmic strings in the first place. Unlike black holes or neutron stars, which leave clear signatures in the form of light or gravitational waves, cosmic strings are incredibly elusive. They might reveal themselves through subtle effects, like causing distortions in the light from distant galaxies or creating ripples in the cosmic microwave background, the faint afterglow of the Big Bang. But so far, no direct evidence of cosmic strings has been found, leaving them firmly in the realm of theory. Even if we could detect cosmic strings, there's the question of whether they could be harnessed for travel. The energy required to interact with these structures would be astronomical, and the risks of instability or collapse could make them too dangerous to approach. But the potential rewards are immense. Cosmic strings could connect distant star systems, allowing us to explore the galaxy without the constraints of time or distance. Beyond their potential for travel, cosmic strings could also offer insights into the fundamental structure of the universe. Studying these hypothetical structures might help us understand the early moments of the Big Bang, the nature of space-time, and even the forces that hold the cosmos together. They remind us that the universe is full of hidden pathways waiting to be discovered and explored. So, could cosmic strings be the ultimate shortcut through the cosmos? While the answer remains uncertain, the journey to find out is a thrilling reminder of how much we still have to learn about the universe. These invisible threads woven into the fabric of space-time challenge us to think beyond the limits of our current knowledge and imagine a future where the stars are no longer out of reach. And in that challenge lies the spark of discovery, pushing us ever closer to the mysteries that await us among the stars. What if the pursuit of faster-than-light travel doesn't just open the door to distant stars, but also to a journey through time itself? This might sound like the plot of a science fiction novel, but it's a very real possibility rooted in the laws of physics. When we talk about traveling faster than light, we're not just talking about breaking the cosmic speed limit, we're talking about bending the rules of time as we know them. The connection between faster-than-light travel and time travel is more than just theoretical. It's a direct consequence of Einstein's theory of relativity, which tells us that time and space are deeply intertwined. Let's break this down. According to relativity, as an object approaches the speed of light, time for that object slows down relative to everything else. This phenomenon, known as time dilation, means that a traveler moving at near light speeds could experience just a few years while decades or even centuries pass on Earth. But what happens if we go beyond the speed of light? Some theories suggest that faster-than-light travel could flip this effect on its head, allowing travelers to arrive at their destination before they even left. In other words, moving faster than light might not just take us to distant stars, it could take us to different points in time. Now, this idea isn't without its complications. One of the most famous is the grandfather paradox, which asks, what happens if you travel back in time and prevent your own existence? If faster-than-light travel enables time travel, could we accidentally alter the course of history in ways we can't predict or control? These questions aren't just philosophical, they're deeply practical. For example, if a mission to a distant star system involves traveling through time, how do we ensure that the crew returns to a timeline that aligns with their original reality? Then there's the ethical dimension. If time travel becomes a reality, who gets to control it? Could it be used to rewrite history, or even to exploit the past for personal or political gain? These dilemmas raise profound questions about responsibility and the limits of human ambition. After all, the ability to manipulate time isn't just a scientific challenge, it's a moral one. But time travel isn't just about paradoxes and ethics. It could also offer practical benefits for interstellar exploration. Imagine a future where spacecraft not only travel faster than light, but also use time dilation to their advantage. A crew could embark on a mission to a distant star system, experience only a few years of subjective time, and return to Earth to find that centuries have passed. This could allow humanity to explore the galaxy without the burden of generational ships or the fear of losing touch with home. Of course, the challenges are immense. We're still far from understanding how to achieve faster than light travel, let alone the complexities of time manipulation. But the very possibility pushes us to think bigger, challenging our assumptions about what's possible and inspiring us to explore the deepest mysteries of the universe. So, could faster than light travel take us not just to the stars, but through time itself? The answer lies in the delicate interplay between science and imagination. As we continue to push the boundaries of what we know, we're reminded that the universe is full of surprises, and sometimes the most extraordinary journeys are the ones that take us not just across space, but through the very fabric of time. What if the fuel for interstellar travel wasn't something we had to carry with us, but instead something we could harvest along the way? This is the bold idea behind interstellar ramjets, a concept that could revolutionize how we think about exploring the cosmos. Unlike traditional spacecraft that carry all their fuel from the start, interstellar ramjets are designed to collect hydrogen atoms from the vast emptiness of space and use them as fuel. By scooping up this abundant resource, these theoretical ships could travel vast distances without the need for massive fuel tanks, unlocking the potential for continuous acceleration and ultimately near light speeds. At the heart of an interstellar ramjet is a massive funnel-like structure, often called a ramscoop, which collects hydrogen atoms as the ship moves through space. These atoms are then funneled into a fusion reactor where they're compressed and heated to extreme temperatures, releasing energy that propels the spacecraft forward. Think of it like a cosmic vacuum cleaner, sucking in fuel as it goes and using it to power an endless journey. The beauty of this system is that it doesn't rely on finite fuel reserves. Instead, it taps into the nearly limitless supply of hydrogen scattered throughout the galaxy. But how fast could such a ship go? In theory, an interstellar ramjet could achieve continuous acceleration, gradually building up to a significant fraction of the speed of light. This means that over time, the ship could cover immense distances without the need for frequent refueling or lengthy stops. A journey to the nearest star system, Alpha Centauri, which would take tens of thousands of years with current propulsion methods, could potentially be reduced to just a few decades or even less. Of course, the challenges of building and operating an interstellar ramjet are immense. One of the biggest hurdles is the sheer scale of the ramscoop required. To collect enough hydrogen to sustain continuous acceleration, the scoop would need to be hundreds or even thousands of kilometers wide, a structure far larger than anything humanity has ever built. Then there's the issue of efficiency. Space is vast and hydrogen atoms are incredibly sparse, meaning the ramjet would need to travel at high speeds just to gather enough fuel to keep going. Another major challenge is the fusion reactor itself. While fusion is a powerful energy source, creating a reactor compact and efficient enough to fit on a spacecraft is no small feat. Current fusion technology is still in its early stages, and scaling it up for interstellar travel would require breakthroughs in both physics and engineering. Despite these obstacles, the potential of interstellar ramjets is too exciting to ignore. They represent a radical shift in how we approach space travel, moving away from the limitations of fuel storage and toward a model of sustainability. By harnessing the resources of space itself, these ships could open up the galaxy to exploration, making distant star systems accessible in ways we've only dreamed of. But the implications go even further. If we could perfect the technology behind interstellar ramjets, it wouldn't just change how we travel, it could change how we think about our place in the universe. By relying on the natural resources of space, we'd be taking the first steps toward becoming a truly interstellar species, one that doesn't just visit the stars but lives among them. So, could interstellar ramjets be the key to unlocking the galaxy? While the challenges are daunting, the possibilities are as vast as the cosmos itself. These theoretical ships remind us that the universe is full of untapped potential, waiting for the right combination of ingenuity and ambition to bring it to life. And as we continue to explore these ideas, we're reminded that the journey to the stars isn't just about reaching new worlds, it's about reimagining what's possible. What if the very fabric of space-time isn't smooth and continuous, but instead a bubbling, frothy sea of turbulence at the smallest scales? This is the mind-bending concept of quantum foam, a theoretical framework that suggests space-time is not the serene, unbroken expanse we imagine, but a chaotic, ever-shifting landscape at the quantum level. At these infinitesimally small scales, space-time is thought to fluctuate wildly, with tiny bubbles of energy popping in and out of existence like foam on the surface of an ocean. These fluctuations are so small and fleeting that they're impossible to observe directly, yet they could hold the key to unlocking entirely new ways of moving through the universe. To grasp the idea of quantum foam, think of space-time as a calm lake. From a distance, the surface appears smooth and unbroken, but if you zoom in close enough, you'll see ripples, waves, and tiny bubbles forming and disappearing. Quantum foam is like those microscopic bubbles, but instead of water, it's the fabric of space-time itself that's churning. These fluctuations are driven by the uncertainty principle, a cornerstone of quantum mechanics, which tells us that energy and time can't both be precisely measured at the same time. This inherent uncertainty creates a kind of turbulence, making space-time resemble a frothy, dynamic sea. Now, imagine if we could somehow harness this quantum foam to create shortcuts through space-time. If space-time is already bubbling and fluctuating at the smallest scales, could we manipulate these fluctuations to open up pathways that bypass the vast distances between stars? Some theories suggest that quantum foam could contain tiny wormholes, microscopic tunnels that connect distant points in space-time. While these wormholes would be far too small to traverse as they naturally occur, the idea is that we might one day find a way to stabilize and enlarge them, turning quantum foam into a cosmic shortcut. But the challenges are immense. For one, quantum foam operates at scales so small that they're far beyond our current ability to observe or interact with. The fluctuations happen over distances measured in Planck lengths, units so tiny that they're a trillion times smaller than an atom. To manipulate quantum foam, we'd need technology capable of operating at these inconceivably small scales, something that's far beyond our current capabilities. Then there's the question of energy. The fluctuations in quantum foam are driven by immense amounts of energy packed into extremely small volumes. To harness or stabilize these fluctuations, we'd need to control energy densities that are almost unimaginable. It's like trying to catch a single bubble in a frothing sea, except the foam is space-time itself, and the bubbles are portals to other parts of the universe. Despite these hurdles, the concept of quantum foam opens up a world of possibilities. It challenges us to think about space-time not as a static stage, but as a dynamic, ever-changing entity. Could these tiny fluctuations be the key to faster-than-light travel, offering a way to traverse the cosmos without the constraints of distance or time? Or are they simply a reminder of how much we still have to learn about the universe's deepest mysteries? As we explore these ideas, we're reminded that the cosmos is full of surprises. Quantum foam may be a distant and elusive concept, but it inspires us to keep pushing the boundaries of what we know. It's a reminder that sometimes the most extraordinary solutions are hidden in the smallest, most chaotic places. And in those places, we might just find the keys to unlocking the stars. What if the universe we perceive with its stars, planets, and galaxies isn't the full picture, but merely a projection of something far simpler? This is the astonishing idea behind the holographic principle, a theory that suggests our three-dimensional reality might be encoded on a two-dimensional surface like a cosmic hologram. Imagine the universe as a movie projected onto a vast screen. What we see as three-dimensional space might actually be information stored on a flat surface, with every star, every planet, and every galaxy represented as data points in this grand cosmic code. At first glance, this might sound like something out of science fiction, but the holographic principle is rooted in serious physics. It emerged from the study of black holes, where scientists discovered that all the information about objects falling into a black hole could be encoded on its event horizon, the two-dimensional boundary surrounding it. This led to the radical idea that the entire universe could work the same way, with all the information about our three-dimensional reality stored on a two-dimensional surface at its edges. So, how does this relate to faster-than-light travel? If the universe is indeed a hologram, then the key to interstellar exploration might lie in manipulating the underlying code of reality. Instead of traversing vast distances in three-dimensional space, we could theoretically access shortcuts by interacting with the two-dimensional surface where the universe's information is stored. It's like rewriting the script of a movie to change the plot. By altering the data on the cosmic screen, we could potentially rewrite the rules of space and time, allowing for travel that bypasses the constraints of light speed. The implications of this idea are staggering. If the universe is a hologram, then space-time itself might be far more malleable than we currently understand. Instead of being bound by the rigid framework of three dimensions, we could explore the possibility of accessing higher dimensional pathways or even creating temporary glitches in the cosmic code to facilitate faster-than-light travel. Imagine a spacecraft that doesn't move through space in the traditional sense, but instead navigates by rewriting the holographic data that defines its position. Of course, the challenges are immense. For one, we're still far from understanding how to interact with this hypothetical two-dimensional surface, let alone manipulate it. The holographic principle is a theoretical framework, and while it's supported by mathematical models, it remains unproven. Even if it's true, the energy and technology required to rewrite the cosmic code would be beyond anything we can currently imagine. But the potential is too compelling to ignore. The holographic principle challenges us to rethink the very nature of reality, pushing us to consider that the universe might be far more interconnected and programmable than we ever thought possible. Could this be the key to unlocking faster-than-light travel? Could the universe itself be the ultimate map guiding us to the stars through its hidden code? As we explore these ideas, we're reminded that the cosmos is full of mysteries waiting to be unraveled. The holographic principle isn't just a theory, it's a window into a universe that's stranger and more wondrous than we often assume. And in that strangeness lies the potential for discovery, pushing us to keep asking questions, keep exploring, and keep dreaming of a future where the stars are no longer out of reach. So, could the universe be a hologram, and could we one day use its hidden code to travel faster than light? The answer lies in the intersection of science and imagination, where the boundaries of what we know blur with the possibilities of what could be. And in that space, we might just find the keys to unlocking the cosmos itself. What if the energy to power faster-than-light travel was already all around us, hidden in the very fabric of space itself? This is the tantalizing promise of zero-point energy, a concept rooted in quantum mechanics that suggests even the emptiest vacuum of space is teeming with energy. Unlike traditional energy sources, zero-point energy doesn't come from burning fuel or splitting atoms. Instead, it's the baseline energy that exists in a quantum system, even when it's at its lowest possible state. Picture it like a quiet hum in the background of the universe, a constant vibration that never stops, no matter how cold or empty space might seem. At its core, zero-point energy arises from the uncertainty principle, which tells us that particles at the quantum level are never completely still. Even in a perfect vacuum where you'd expect nothingness, particles flicker in and out of existence, creating a sea of energy that's always present. This isn't just a theoretical curiosity, it's been experimentally observed in phenomena like the Casimir Effect, where two uncharged plates placed incredibly close together experience a subtle force due to these quantum fluctuations. So, how could this energy be used for faster-than-light travel? The idea is to tap into this constant, inexhaustible source of power to propel spacecraft without the need for traditional fuel. Imagine a ship that draws its energy directly from the vacuum of space, using the hum of quantum fluctuations to generate thrust. This would eliminate the need to carry massive fuel reserves, making interstellar voyages lighter, faster, and more efficient. The implications are staggering. A spacecraft powered by zero-point energy could, in theory, achieve continuous acceleration, pushing ever closer to the speed of light without ever running out of fuel. But the challenges of harnessing zero-point energy are just as immense as its potential. For one, the energy density of these quantum fluctuations is incredibly low. While the vacuum is full of energy, it's spread so thinly that extracting enough to power a spacecraft would require technology far beyond our current capabilities. Some estimates suggest that the energy in a cubic meter of vacuum is equivalent to the mass of a single proton, hardly enough to move a feather, let alone a starship. Another major hurdle is the issue of control. Zero-point energy is inherently chaotic, with particles popping in and out of existence at random. To harness it, we'd need a way to stabilize and direct this energy, turning quantum noise into a usable source of propulsion. This would likely require breakthroughs in quantum field theory, materials science, and energy conversion fields that are still in their infancy. Despite these obstacles, the potential rewards are too compelling to ignore. Zero-point energy represents a radical departure from traditional propulsion methods, offering a way to explore the cosmos without the limitations of fuel storage or energy scarcity. If we could master this technology, it could revolutionize not just space travel, but our entire approach to energy and sustainability. But the implications go beyond practicality. Tapping into zero-point energy would fundamentally change how we understand the universe. It would show us that even emptiness is full of potential, that the void of space is anything but empty. It challenges us to rethink the nature of energy itself, pushing the boundaries of what we think is possible. Could zero-point energy be the key to unlocking faster-than-light travel? While the answer remains uncertain, the journey to explore this quantum hum is a testament to humanity's relentless curiosity and ambition. As we continue to probe the mysteries of the universe, we're reminded that sometimes the most extraordinary solutions are hidden in the quietest places. And in those places, we might just find the keys to the stars. What if our universe is just one of countless others, each with its own stars, planets, and perhaps even life? This is the mind-expanding idea behind the multiverse theory, a concept that suggests our cosmos is just a single bubble in an infinite sea of parallel universes. These universes might exist alongside ours, separated by the thinnest of barriers, or they could be entirely different realities with their own laws of physics. The possibilities are as vast as the multiverse itself, and if faster-than-light travel were possible, it might not just take us to distant stars, but to entirely new realities beyond our own. The multiverse theory comes in many forms, but one of the most compelling is the idea of a bubble multiverse. Imagine our universe as a bubble floating in a vast cosmic foam, with countless other bubbles surrounding it, each representing a separate universe. Some of these universes might be nearly identical to ours, with only subtle differences, while others could be wildly different, governed by entirely unfamiliar laws of physics. The question is, how could we cross the void between these bubbles? This is where faster-than-light travel comes into play. If we could find a way to move beyond the speed of light, we might be able to pierce the boundaries between universes, traveling from one bubble to another. One possibility is that faster-than-light travel could create a kind of bridge or wormhole between universes, allowing us to step from one reality into the next. It's a concept that sounds like science fiction, but it's rooted in the same physics that describe wormholes and warp drives. The key difference is that instead of connecting 2 points in our own universe, these bridges would link entirely separate realities. But the challenges are immense. For one, we have no way of detecting parallel universes directly. They're hidden from us either because they're too far away in a higher dimensional space or because they're fundamentally inaccessible from our own reality. Even if we could detect them, the energy required to cross between universes would be staggering far beyond anything we could generate with current technology. And then there's the question of stability. Would these bridges between universes hold long enough for travel, or would they collapse, trapping travelers in the void between realities? The implications of multiverse travel go far beyond exploration. If we could access parallel universes, we might find worlds where the laws of physics are radically different, offering new ways to generate energy, manipulate matter, or even rewrite the rules of reality. We might encounter civilizations that have developed technologies far beyond our own, or discover versions of Earth where history took a different path. The multiverse could be a treasure trove of knowledge, culture, and resources, but it could also be a place of unimaginable dangers. And then there's the philosophical dimension. If the multiverse exists, what does that mean for our understanding of reality? Are there infinite versions of ourselves living out every possible life in every possible universe? Could we meet these alternate versions, or would they remain forever out of reach? These questions challenge us to rethink not just how we explore the cosmos, but how we define our place within it. The multiverse theory is more than just a scientific idea. It's a gateway to infinite possibilities. It challenges us to imagine a reality where the stars are just the beginning, and the true frontier lies in the spaces between universes. Could faster-than-light travel be the key to unlocking this ultimate frontier? While the answer remains uncertain, the journey to explore these ideas is a testament to humanity's boundless curiosity and our relentless drive to push the boundaries of what's possible. As we ponder the mysteries of the multiverse, we're reminded that the cosmos is full of surprises, waiting for us to uncover them. Whether or not we ever step into a parallel universe, the very idea inspires us to dream bigger, to explore farther, and to keep reaching for the stars and perhaps beyond them. What if the key to faster-than-light travel lies in solving one of the greatest mysteries in physics? Enter quantum gravity, a theory that aims to bridge the gap between two seemingly incompatible pillars of modern science, Einstein's general relativity and quantum mechanics. General relativity describes the universe on a grand scale, explaining how massive objects like stars and galaxies warp space-time. Quantum mechanics, on the other hand, governs the behavior of the smallest particles, revealing a world of uncertainty and probability. But when it comes to understanding the universe as a whole, these two theories don't play nicely together. Quantum gravity seeks to unify them, offering a single framework that could revolutionize our understanding of space, time, and reality itself. At the heart of quantum gravity is the idea that space-time isn't smooth and continuous, as general relativity suggests, but instead made up of tiny, discrete units. Think of it as the universe's version of pixels. These units, often called quantum foam, are so small that they're impossible to observe directly, but they could hold the key to unlocking entirely new ways of manipulating space-time. If we could understand and control these quantum-scale fluctuations, we might be able to create shortcuts through the fabric of the universe, enabling faster-than-light travel without breaking the cosmic speed limit. But developing a theory of quantum gravity is no small task. For decades, physicists have struggled to reconcile the deterministic nature of general relativity with the probabilistic world of quantum mechanics. The math becomes incredibly complex, and the predictions often seem to defy common sense. One leading candidate for a quantum gravity theory is string theory, which proposes that the fundamental building blocks of the universe aren't particles but tiny, vibrating strings. These strings exist in higher dimensions, and their vibrations give rise to everything we see, from particles to forces. Another contender is loop quantum gravity, which suggests that space-time itself is woven together in a network of loops. Both approaches offer tantalizing glimpses of a unified theory, but neither has yet been proven. The challenges don't end there. Even if we could develop a complete theory of quantum gravity, applying it to faster-than-light travel would require technology far beyond our current capabilities. We'd need to manipulate space-time at the smallest scales, creating and stabilizing structures like wormholes or warp bubbles. This would demand not only a deep understanding of quantum gravity, but also the ability to generate and control immense amounts of energy. It's like trying to build a bridge between two distant islands, but without knowing the exact shape of the ocean floor beneath. Yet the potential rewards are too extraordinary to ignore. A unified theory of quantum gravity could unlock entirely new ways of exploring the cosmos. Imagine being able to bend space-time at will, creating pathways that bypass the vast distances between stars. Or consider the possibility of harnessing quantum fluctuations to power spacecraft, tapping into the very fabric of the universe itself. These ideas might sound like science fiction, but they're rooted in the cutting-edge research of today. Beyond its implications for space travel, quantum gravity could also answer some of the deepest questions about the universe. What happens at the center of a black hole? What was the universe like in the first moments after the Big Bang? Could there be other dimensions hidden from our view? These are the mysteries that quantum gravity seeks to unravel, offering a glimpse into the inner workings of reality itself. So, could quantum gravity be the key to unlocking faster-than-light travel? While the answer remains uncertain, the journey to find it is a testament to humanity's unyielding curiosity and ambition. As we continue to probe the mysteries of the universe, we're reminded that sometimes the most extraordinary breakthroughs come from asking the toughest questions. And in those questions, we might just find the keys to the stars, and perhaps even the universe itself. What if the co-pilot for humanity's journey to the stars wasn't human at all, but a machine capable of thinking faster and seeing farther than we ever could? Artificial intelligence, or AI, is poised to become an indispensable ally in the quest for faster-than-light travel, offering solutions to some of the most daunting challenges of interstellar exploration. From designing spacecraft that push the limits of physics to navigating the unpredictable twists and turns of space-time, AI could revolutionize how we approach the cosmos. But how exactly could this technology transform the future of space travel, and what challenges might we face along the way? Imagine a spacecraft equipped with an AI system capable of processing vast amounts of data in real time, analyzing everything from fuel efficiency to gravitational anomalies. Unlike human pilots who are limited by reaction times and cognitive biases, AI could make split-second decisions based on complex calculations, optimizing every aspect of the journey. For instance, an AI-powered propulsion system could adjust thrust levels with pinpoint precision, ensuring maximum efficiency while conserving energy. It could also predict and avoid cosmic hazards like asteroid fields or radiation storms, keeping the crew safe in the unforgiving void of space. But the role of AI goes beyond just navigation and safety. Designing a spacecraft capable of faster-than-light travel is a monumental task requiring engineers to balance countless variables, from energy consumption to structural integrity. AI could streamline this process by simulating millions of design iterations, identifying the most efficient configurations and flagging potential flaws long before construction begins. This would not only save time and resources, but also push the boundaries of what's possible, leading to breakthroughs that might otherwise take decades to achieve. One of the most exciting possibilities is AI's ability to decode the mysteries of space-time itself. Faster-than-light travel often involves manipulating the fabric of the universe, whether through warp drives, wormholes, or other theoretical constructs. These concepts rely on highly complex mathematics and physics, far beyond the capacity of human minds to fully grasp. AI, however, could analyze these models, identify patterns, and even propose new solutions that we haven't yet considered. It's like having a co-pilot who not only understands the roadmap but can also redraw it on the fly. Of course, integrating AI into space exploration isn't without its challenges. One of the biggest concerns is reliability. Space is an unpredictable environment, and even the most advanced AI systems could encounter errors or malfunctions. Ensuring that these systems are robust enough to handle the rigors of interstellar travel will require rigorous testing and fail-safes. There's also the question of autonomy. How much control should AI have over critical systems, and how do we ensure that it aligns with human goals and values? These are ethical and technical dilemmas that will need to be addressed as we move forward. Despite these hurdles, the potential of AI in space exploration is too significant to ignore. It could open up entirely new possibilities for faster-than-light travel, making the stars more accessible than ever before. And it's not just about the technology. AI could also enhance our understanding of the universe, helping us uncover the secrets of space-time, dark matter, and other cosmic mysteries. So, could AI be the ultimate co-pilot for interstellar journeys? The answer lies in the delicate balance between human ingenuity and machine intelligence. As we continue to develop and refine these systems, we're reminded that the journey to the stars isn't just about building faster ships, it's about creating smarter ones. With AI by our side, the cosmos might just become a little less distant and a lot more within reach. What if the secret to surviving the vast distances of interstellar travel lies in slowing life down to a standstill? Enter cryogenics, the science of preserving life at ultra-low temperatures, offering a potential solution to one of the most daunting challenges of space exploration: time. Cryogenic sleep, often depicted in science fiction, isn't just a futuristic fantasy, it's a field of serious scientific research that could allow humans to endure the centuries-long journeys between stars. By freezing biological processes, cryogenics could effectively hit the pause button on aging, enabling astronauts to wake up in distant star systems just as they left, biologically unchanged. The concept of cryogenic sleep hinges on the idea of reducing the body's metabolic rate to near zero. At temperatures close to absolute zero, the chemical reactions that drive aging and cellular decay slow to a crawl, effectively halting the biological clock. Imagine a spacecraft where the crew enters a state of suspended animation, their bodies preserved in a deep freeze as the ship travels through the void. When they arrive at their destination, advanced systems would gently revive them, ready to explore a new world. It's a concept that transforms the idea of generational ships, where multiple generations live and die during the journey, into something more personal and immediate. But how feasible is this technology? Cryogenics has already shown promise in preserving cells, tissues, and even small organisms, but scaling it up to human beings presents a host of challenges. One of the biggest hurdles is preventing ice crystal formation, which can damage cells and tissues during freezing and thawing. To solve this, scientists are exploring cryoprotectants chemicals that act like antifreeze, preventing ice from forming and keeping cells intact. Another challenge is reviving the body without causing harm. The process of cooling and warming must be carefully controlled to avoid thermal shock, which could damage organs or disrupt vital functions. Beyond the technical challenges, there's also the question of psychological impact. How would humans cope with the experience of being frozen for years, decades, or even centuries? Would they wake up disoriented, their memories intact but the world around them radically changed? These are questions that touch on the very nature of identity and consciousness, raising ethical and philosophical dilemmas that go beyond the realm of science and engineering. Yet the potential rewards are immense. Cryogenics could make interstellar travel not just possible but practical. By slowing down the biological effects of time, it could allow humans to explore distant star systems without the burden of aging or the need for generational ships. And while cryogenics alone doesn't solve the problem of faster-than-light travel, it could complement other technologies like warp drives or wormholes by ensuring that the crew arrives at their destination in peak condition. Could cryogenics be the key to unlocking the stars? While the challenges are significant, the possibilities are too compelling to ignore. It's a reminder that sometimes the most extraordinary solutions come from rethinking the basics, like the way we experience time itself. As we continue to explore the frontiers of cryogenics, we're reminded that the journey to the stars isn't just about building faster ships. It's about finding new ways to preserve and protect the most precious cargo of all, human life. So, as we dream of a future where the stars are within our reach, cryogenics stands as a testament to our ingenuity and determination. It challenges us to think beyond the limits of biology and time, offering a glimpse of a future where the cosmos isn't just a place to visit, but a journey we can truly experience. And in that journey, we might just find the keys to unlocking the greatest adventure of all. What if the key to faster-than-light travel isn't just about moving through space, but reshaping it entirely? This is the bold vision of space-time engineering, a field that pushes the boundaries of physics to manipulate the very fabric of the universe. Imagine being able to bend, fold, or even stitch together space-time itself, creating pathways that bypass the vast distances between stars. It's not just a dream, it's a concept grounded in the laws of physics, and one that could redefine how we explore the cosmos. At its core, space-time engineering is about harnessing the malleability of the universe. According to Einstein's theory of general relativity, space-time isn't a rigid stage, it's a dynamic, flexible fabric that can be warped by mass and energy. This means that, in theory, we could create structures like warp bubbles or wormholes, effectively bending the rules of space and time to our advantage. A warp bubble, for example, compresses space in front of a spacecraft while expanding it behind, allowing the ship to surf through space-time without actually breaking the speed of light. Wormholes, on the other hand, act as shortcuts connecting distant points in the universe through a tunnel-like structure. But how could we build such structures? The answer lies in advanced technologies that manipulate energy and matter on a cosmic scale. One approach involves exotic matter, a theoretical substance with negative energy density that could stabilize wormholes or power warp bubbles. Another possibility is harnessing the energy of quantum fluctuations or even dark energy, the mysterious force driving the universe's expansion. These ideas might sound like science fiction, but they're based on real physics that's still waiting to be fully understood and harnessed. The challenges, of course, are immense. For one, the energy requirements are staggering. Creating a warp bubble or stabilizing a wormhole would demand amounts of energy comparable to that of an entire star or even more. Then there's the issue of control. Space-time engineering isn't just about generating energy. It's about directing it with precision, ensuring that the structures we create are stable and safe for travel. Even the smallest miscalculation could lead to catastrophic consequences, from collapsing wormholes to runaway warp bubbles. Yet, the potential rewards are too extraordinary to ignore. Space-time engineering could make interstellar travel not just possible but practical. Imagine a future where spacecraft don't just travel through space, they reshape it, creating pathways that bring distant stars within reach. This isn't just about exploring new worlds, it's about redefining our relationship with the universe itself. By mastering space-time engineering, we could unlock a future where the cosmos isn't a vast, untouchable expanse, but a dynamic playground of infinite possibilities. But what would it take for humanity to reach this level of technological sophistication? Some scientists speculate that space-time engineering might be the hallmark of advanced civilizations, perhaps even a Type Roman III civilization on the Kardashev scale, capable of harnessing the energy of an entire galaxy. For now, we're far from that level of development, but the journey to get there is already underway. From groundbreaking experiments in quantum physics to theoretical explorations of warp drives and wormholes, the seeds of space-time engineering are being planted today. So, could space-time engineering be the ultimate tool for faster-than-light travel? While the answer remains uncertain, the pursuit of this idea is a testament to humanity's unyielding curiosity and ambition. It challenges us to think beyond the limits of our current understanding, to imagine a future where the stars are no longer out of reach. And in that challenge lies the spark of discovery, pushing us ever closer to the mysteries that await us among the stars. As we continue to explore the frontiers of space-time engineering, we're reminded that the universe is full of surprises, and sometimes the most extraordinary solutions are hidden in the smallest, most chaotic places. And in those places, we might just find the keys to unlocking the stars. What if the universe is teeming with life, but we're just not seeing it? This is the heart of the Fermi paradox, a question that has puzzled scientists and dreamers alike for decades. Named after physicist Enrico Fermi, who famously asked, "Where is everyone?" the paradox highlights a striking contradiction. Given the sheer size and age of the universe, why haven't we encountered any signs of extraterrestrial civilizations? With billions of stars and potentially habitable planets in our galaxy alone, the odds seem overwhelmingly in favor of life existing elsewhere, yet the silence is deafening. Could faster-than-light travel hold the key to solving this cosmic mystery? One possible explanation for the Fermi paradox is the immense difficulty of interstellar travel. Even with advanced technology, the distances between stars are so vast that communication or travel between civilizations might be nearly impossible within a human lifetime. Without faster-than-light travel, civilizations could remain isolated, each confined to their own corner of the galaxy. Imagine trying to shout across an ocean. No matter how loud you are, the message might never reach the other side. Faster-than-light travel could change this, allowing civilizations to bridge these cosmic gaps and make contact with one another. But there's another intriguing possibility. What if advanced civilizations are already out there, but they're hiding? Some theories suggest that highly advanced aliens might avoid detection intentionally, either to observe us without interference or to protect themselves from potential threats. If faster-than-light travel were possible, it could enable these civilizations to remain hidden in ways we can't yet comprehend. They might use technologies like cloaking devices or warp bubbles to move undetected through the cosmos, leaving no trace of their presence. The implications of the Fermi paradox for faster-than-light travel are profound. If we could develop the ability to travel faster than light, we might finally break through the barriers that keep civilizations apart. It could allow us to explore distant star systems, search for signs of life, and perhaps even make contact with other intelligent beings. But it also raises questions about our own role in the universe. Are we alone, or are we simply too primitive to join the cosmic conversation? Another angle to consider is the possibility that faster-than-light travel itself could explain the paradox. If advanced civilizations have already mastered this technology, they might have moved beyond our current understanding of space and time. They could exist in dimensions or realms we can't perceive, making them invisible to us. It's like trying to spot a fish in a pond from the surface. Unless you dive beneath the water, you'll never see what's really there. Ultimately, the Fermi paradox challenges us to think bigger and dig deeper. It's not just about finding other life in the universe, it's about understanding our place within it. Faster-than-light travel could be the tool that unlocks these answers, allowing us to explore the cosmos in ways we've only dreamed of. But it also reminds us that the universe is full of mysteries, and some of them might remain just out of reach, no matter how advanced our technology becomes. Could faster-than-light travel solve the Fermi paradox? The answer lies somewhere between the stars and the limits of our imagination. As we continue to explore the cosmos, we're reminded that the journey is as important as the destination. And in that journey, we might just find the answers we've been searching for, or uncover even greater questions waiting to be asked. As we wrap up this cosmic journey through 30 astonishing theories on faster-than-light travel and interstellar voyages, one undeniable truth emerges. The universe is a treasure trove of mysteries and possibilities, just waiting for us to uncover them. From the mind-bending potential of wormholes to the revolutionary ideas behind warp drives, each theory we've explored challenges not only the limits of physics but also the boundaries of our imagination. These concepts, while still largely theoretical, remind us that science is a living, breathing field, one that grows, evolves, and surprises us with every discovery. What makes this exploration so thrilling is the sheer diversity of ideas on the table. Whether it's harnessing the power of exotic matter to stabilize wormholes or riding gravitational waves like cosmic surfers, each theory offers a unique lens through which we can glimpse the future of space travel. Some ideas, like the Alcubierre Warp Drive, are rooted in well-established physics, while others, like quantum tunneling or hyperspace, push us to think beyond the familiar and into the realm of the extraordinary. Yet, as exciting as these theories are, they also come with a healthy dose of humility. Many of these concepts remain untested, and the challenges they present, whether it's the mind-boggling energy requirements of warp bubbles or the elusive nature of exotic matter, are immense. But isn't that the beauty of science? It's not about having all the answers. It's about asking the right questions, daring to dream, and pushing forward even when the path ahead is uncertain. The dream of faster-than-light travel isn't just about reaching distant stars. It's about redefining what it means to be human. It's about stepping beyond the confines of our planet and embracing the cosmos as our true frontier. It's about curiosity, courage, and the unshakable belief that there's always more to discover. And while we may not achieve these breakthroughs in our lifetimes, the journey itself is just as important as the destination. Every equation solved, every experiment conducted, and every theory tested brings us one step closer to unlocking the secrets of the universe. So, as we close this chapter, I want to leave you with a question. Which of these theories excites you the most? Is it the elegance of wormholes, the audacity of warp drives, or perhaps the mind-bending potential of quantum foam? Let me know your thoughts in the comments below. I'd love to hear your ideas and spark a conversation. And if you've enjoyed this journey through the cosmos, don't forget to subscribe and hit that notification bell for more deep dives into the mysteries of the universe. The stars are calling, and with each new discovery, we're coming closer to answering. Until then, let's keep dreaming, keep exploring, and keep reaching for the infinite possibilities that lie beyond the horizon. The cosmos is vast, but so is our potential. Together, who knows what we might achieve? Thanks for joining me on this adventure. See you among the stars.